I'm delighted to say that our next speaker in the Kuhn 100 conference is a keynote presentation from Professor Hanne Andersen in the University of Copenhagen. We're delighted to have her here, and her joint work on Kuhn, on cognitive science in science discovery has been just amazing. So wonderful to meet you in person for the first time, and hopefully just as the other speakers in the conference, we can somehow get you to come to Bucharest in a future event that might be coming up very soon. Professor Andersen's talk is titled "The Structure and Development of 21st Century Science." Professor Andersen, please take it over.
Thank you very much, and thank you very much for inviting me to this event. I'm happy that it was possible to participate online, but I do indeed hope that at some point in the future, it'll be possible to be present or in person. This event on Kuhn's 100th is a wonderful event. One of the most important and at the same time also most controversial books in philosophy of science in the 20th century has been The Structure of Scientific Revolutions, authored by Kuhn in 1962. Impressively, for a book in philosophy of science, Structure seems to have sold more than 1 million copies. Figures differ a little bit between authors, but whether it's 1 million or 1.1 or 0.9, I think it's numbers that the rest of us can only dream about. And during the 60 years that have passed since the publication of Structure, really a lot of work here, just a selection in history and philosophy of science, has been dedicated to interpreting, criticizing, or defending Kuhn's account of how science develops. So it's had a significant influence on history, philosophy, and sociology of science. Some will find it for the better, others will find it for the worse. But I think it's important also to realize that its influence spans much broader than that. The fact that so many copies of Structure have been sold and circulated also means that it has been read by many, many people outside of history and philosophy of science. It has been read by many scientists, science educators, science managers, and policymakers. And through this route, it has also contributed to determining the conditions for how science developed after the publication of Structure as we moved out of the 20th and into the 21st century. And I'll show here just one example, the way the National Science Foundation describes their support of transformative research, which is for them an important area to support, and the way they define transformative research. Transformative research challenges current understandings, provides pathway to new frontiers in science and engineering, involves ideas, discoveries, or tools that do one or both of the following: either radically change understanding or lead to the creation of a new paradigm or field of science, engineering, and education. So there's no doubt that for a lot of our funding agencies and in similar places, this idea of paradigms and paradigm shifts has actually become an important part of their thinking. That also means that it's important to think about Structure was written 60 years ago, and the analysis it provides, if that is so influential also in science policy, does it still hold today? So let's go back to Kuhn's Structure and start examining how his analysis holds today. In Structure, Kuhn argued that over the course of history, science does not develop cumulatively as it is, for example, often presented in the textbooks and in certain kinds of internalist history, but that instead it develops in phases of cumulative normal science and disruptive revolutions. That descriptive historical claim was revolutionary in itself. And as someone who primarily teaches philosophy of science to science students, I can report that it's still revolutionary for many science students when they first encounter the idea. But Kuhn's aim was not merely descriptive. Kuhn accompanied his historical descriptive claim with a normative philosophical account of why, for the scientific endeavor, as seen as an idealized version from within itself, this phase model of science was an asset to science epistemic advance. And the core of this philosophical account was Kuhn's argument about an essential tension. So here we're back also to Hasek's talk, or about the essential tension between convergent and divergent thought that he had developed prior to the publication of Structure. In this essential tension paper, Kuhn stressed the importance of normal science as a convergent activity that aims at adjusting existing theories and observations in order to bring them into closer and closer agreement, or to extend existing theory to areas that it is expected to cover, but in which it has not been tried before. And he argued that this kind of activity is immensely effective in solving the problems that existing theory defines, and the continuous use of the existing theory therefore enables science to move faster and penetrate deeper than if the theory was continuously questioned or changed. In this way, normal science is a tradition-preserving activity. Yet, again and again, the ultimate effect of this tradition-bound work is a shattering of the same tradition. Kuhn argued that, at least for the scientific community as a whole, work within a well-defined and deeply ingrained tradition seems more productive of tradition-shattering novelties than work in which no similar convergent standards are involved. How can this be so? I think it's because no other sort of work is nearly so well suited to isolate for continuing and concentrated attention those loci of trouble or causes of crisis upon whose recognition the most fundamental advances in basic science depends. And this is exactly the essential tension between tradition and innovation. Without the possibility of divergent thought, fundamental innovation would be precluded. And without a strong emphasis on convergent thought, science would be a total mess created by continuous theory changes, and scientific progress would also be precluded. However, for this tension to work as a mechanism for change, what is also needed is a distribution of conservative and innovative dispositions among the members of the scientific community. And this is something that he addressed in Structure, where he noted that if all members of a community responded to each anomaly as a source of crisis or embraced each new theory advanced by a colleague, science would cease. If, on the other hand, no one reacted to anomalies or brand new theories in high-risk ways, there would be few or no revolutions. This is a very, very short summary of Kuhn's essential tension argument. And the way in which that argument has been usually discussed in the philosophical literature, that has often focused on 3 points, are the effectiveness of normal science, both in solving puzzles and in identifying loci of trouble, or the risk spreading argument, how risk has to be spread among individual members of the community, and how then theory choice is made at the communal level. And then a fourth component here, I agree very much with Hasek, has been less discussed, namely that a special kind of education that serves to enable the other elements is a prerequisite for the Kuhnian model. But additional points are to be noted. First, the epistemic aims that are served on the Kuhnian account are not only to increase the efficiency with which science advances and justifies new knowledge claims, but also the efficiency with which science explores, identifies, and develops promising new research problems and methods for their solution. So that, in a way, enlarges our epistemological concerns from considering primarily obtained results to considering also future promise. And although often overlooked, the Kuhnian account also points to concerns about the efficiency with which science developed human competences and capacities for both of the 2 points above on this list. And that enlarges our epistemological concerns even further. And I think there are a number of assumptions underlying Kuhn's analysis of how science progresses over time that may be historically contingent and which may therefore prompt us now in the 21st century to revisit the analysis and the lessons that we draw from it. First, the effectiveness of normal science in identifying and solving all the problems that a paradigm defines depends on the community members being able to first effectively keep track of the development of their field, Second, to largely trust what other community members have found without having to carry out the same work themselves in its entirety. So it does depend on open communication between a manageable volume of responsible researchers. Second, the effectiveness in locating what Kuhn called loci of trouble depends on community members being first able to pursue every minor detail or leaving no stone untouched, and second, being meticulous in assessing new results, their own as well as the results of others, and third, in a position to raise questions and voice concerns. So there are some prerequisites about the ability to keep working on detailed work and the ability to voice concerns, or there's something about hierarchical structures that may play in here. And finally, for the risk spreading mechanism, that depends on the individual community members being free to pursue alternative directions, even at a point where others do not find it particularly promising. So freedom of research is also one of the prerequisites of a Kuhnian model. And these are all assumptions that may change with changes of volume, changes of what I shall later call the granularity of research activities, changing in front-end patterns, etc. So what I'm in the process actually of doing right now in a larger research project, from which I here report only parts, is to revisit Kuhn's essential tension and analyze how it may change with all the various changing conditions that has happened to science over the last decades. So let's start from these changes. Kuhn and others at the same time analyze the situation of scientists who are working individually, within disciplinary boundaries, who were able to keep track of the development of their specialty, are all actively participating in an organized skepticism anchored in a well-defined community, while being free to pursue the ideas that they found most fruitful and expected to do so with integrity. But since then, science has increased in volume, it's become more collaborative, more interdisciplinary, more dependent on funding and on consideration about usefulness, and more frequently haunted by questionable practices. How do all these structural changes affect the way with which science develops? That is, of course, a question that is much larger than what can be overcome in a single talk, and I'll therefore have to provide only a sketch of some of the major points of my analysis, points related primarily to interdisciplinarity, collaboration, and the granularity of collaboration. So first, collaboration. While Kuhn's historical studies were focused on individual scientists, science today has become increasingly collaborative. Or with some minor variations between disciplines, it has been documented across all scientific disciplines that more and more research is conducted in groups. Or here we see a graph from a publication from published in Science in 2007 that shows the increase in publications that are co-authored by teams, or the black line to the left is for the natural sciences, rising from half of the publications around 1960 to 80% of the publications in the year 2000. And to the right, you see the increase in the mean team size, less than 2 as a mean in 1960, and 3.5 as a mean in the year 2000. Similarly, while Kuhn's historical studies focused on scientists working within disciplinary boundaries, science today has become increasingly interdisciplinary. Various methodologies have been used to document that development, increasing prevalence of co-authors with different disciplinary affiliations, increasing assignment of keywords from different disciplines, increase in citations across disciplinary boundaries, as is showed, for example, by this kind of citation map, or that shows how different disciplines refer to each other. In some of my previous publications, I have argued that if we investigate these developments as a spectrum in 2 dimensions, that range from the disciplinary to the interdisciplinary, and the other dimension from the individual to the collaborative. We can talk about 4 different ideal types of research activities. First, the traditional view, or the traditional legend, of scientists brought up in the same tradition to act as independent and autonomous agents who are individually accountable for their research and together provide a community-based quality control of new results. That's very much the picture painted by Kuhn. At the same time, I refer to it here as a legend because the idea of epistemic independence and autonomy of each agent is a legend, or scientists will always be dependent upon each other in some way or other. But a lot of our thinking has been formed by this idea about independence and epistemic autonomous and our firm quality control by the community. So I also think that another ideal type is a tendency to disciplinize interdisciplinary research by creating new programs that train the next generation in an interdisciplinary field to master all the cognitive resources involved in this research field. So that is an attempt to make sure that although this is a new interdisciplinary field, the practitioners will become epistemically autonomous, individually accountable for their research. There'll be a community-based quality control. So it brings back interdisciplinary research through the traditional legend, or like the disciplines, by creating these omniscient or interdisciplinarians. Third and fourth, as we move to the right, for collaborative research, we have either disciplinary division of labor between scientists who share the same cognitive resources and just divide similar pieces of labor among them because none of them could overcome it all, or interdisciplinary division of labor between scientists from different disciplines who collaborate in order to combine different cognitive resources that are distributed among them and which they do not all possess individually. In both cases, scientists in such collaborations will defer to each other as part of the research process, which means that they are no longer individually fully accountable for the produced results. And further, if they collaborate across disciplinary boundaries, there's not a well-defined community to provide the quality control. The traditional legend has made us think that it's in traditional monodisciplinary activities that we can uphold individual accountability and community-based quality control. And this legend is the basis for much contemporary concern that either see collaboration in interdisciplinarity science as something that is not quite up to standards, or something that is particularly hard and challenging. And then yet, at the same time, more and more science in the 21st century go in the direction of more collaboration and more interdisciplinarity. Elsewhere, I have argued that changing review practices towards more collaborative formats would be one way of rethinking quality control for collaborative interdisciplinary research, and that being much more transparent about calibration of trust among collaborators is one way of rethinking accountability that ought to figure more prominently in the way we teach research integrity and responsible conduct of research. So in this way, I think our philosophical work can be used to give advice for contemporary science in how to deal with some of the challenges they're facing in science becoming more collaborative and more interdisciplinary. What I will be concerned with in the rest of my talk is something that I haven't published yet and which I'm still working on, and which I should call the changing granularity of research activities. As I mentioned previously, science has not only become increasingly collaborative in the sense that more and more research is produced in groups. On average, the size of the groups has also steadily increased, at least if group size is measured by co-authorships. And here is another graph from a report from the National Academy of Sciences from 2015 that shows the increase for different group sizes, where at the top left, You see one author, two author groups started out being the more prevalent. The very red line you can see that starts in the middle to the left is 6 to 10 authors, which was not very prevalent in 1960, but if you go to the right to 2015, it is actually the most prevalent group size. So groups are becoming larger and larger. And I'm talking here about small to medium size teams. I'm not talking about the real big scale teams, or there's a whole literature, of course, on big science, and you can see those are as the two lower curves are to the right, one curve for 100 to 1,000 authors, and one curve, the one to the far most right, are publication with more than 1,000 authors. But that's not my concern. My concern are these colored lines are at the top. So what such scientometric work shows is that scientists do no longer primarily work and publish individually alone, as was the case for most of the examples that Kuhn drew on in structure. We can represent that very idealized here, or in a Kuhnian community, or scientists are individuals, or that can all be treated as equivalent. But today they tend to cluster. They form small to medium-sized teams in their publications. There are still people who work alone, but a lot of them cluster in various ways. So there's a gradual change in what I will call the granularity of the scientific community, the way in which the efforts of scientists is distributed within the community, the way they cluster together. And what does this clustering mean for the tension between tradition and innovation, between convergent and divergent thought? Is there a difference between the situation at the top and the situation at the bottom in this very idealized diagram in how efficient science is in examining and solving the puzzles defined within a paradigm? Or is there a difference in open communication, in the manageability of the volume, and in how to think about responsibility in research? Or here intuitively, or a cluster of closely collaborating scientists seems more efficient for puzzle solving, since they can distribute work among them, than perhaps a lot of people working individually. But further, is a difference between the situation at the top and situation at the bottom in how efficient science is in identifying and isolating for continuing and concentrated attention the loci of trouble, or for the ability to leave no stone left unturned, may be meticulous in assessing all the results that come out, or in the openness for criticism. Intuitively, the difference seems to depend on how open a group or cluster is for internal criticism. And finally, is there a difference between the situation at the top and the situation at the bottom when it comes to risk spreading? Again, intuitively, the difference depends on how open the group or cluster is for trying out alternatives to what they've previously done, with the inbuilt risk that it may void previous achievements. In some, intuitively, clusters seem better or fit for efficient puzzle solving, while it depends on their inner functioning, whether they are as efficient as a community of individual peers for locating loci of trouble and for examining alternative directions while spreading risk. And if that is the case, that may be important for science policy. Many funding schemes favor intermediate to large-scale funding for collaborations, and often these collaborations are organized hierarchically. The picture here is from a textbook in research leadership used at Danish universities, that depicts such a hierarchical organization as a rocket with a single or just a few PIs at the top of the rocket, an intermediate layer of postdocs, and then a huge fuel tank of PhD students whose work is the energy that drives the rocket forward in the direction set by the PI. And that rocket-shaped organization is generally extremely efficient in puzzle solving, in producing impressive amounts of results within a particular area defined by the PI. On current authorship practices, the PI will very often be senior author on all the publications from the rocket, so it's also very efficient in making the top PI gain prominence, whereas the juniors can sometimes be seen almost as a consumable. But it should also be noted that the potential high gain also comes with a high risk if the entire direction turns out wrong. An alternative organization is a constellation of stars in the form of senior researchers from different areas of expertise whose collaboration has the flexibility to adapt to various opportunities that may arise, but is less narrowly focused on in its specialization. That also means that different results may be interesting for different audiences, and hence there's not the same huge and immediate impact in a particular field, and the total impact in several fields can be hard to track. Therefore, this organization is often seen as less efficient, although that may be an artifact of, or because it's just distributed in different fields. But how do the two models actually affect science efficiency in not only solving puzzles, but also identifying loci of trouble and or spreading risk? That depends on the inner structure of such collaborations. And while the inner workings of such teams of groups can be of several kinds, I shall here concentrate on two ideal types, interaction among equal experts and hierarchical integration. These are ideal types that I have previously examined together with Susan Wagenknecht, although we use slightly different names, and where we were also inspired by earlier work by Rossini and Porter, which I want to acknowledge. For hierarchical integrations, the PI acquires input from all group members and synthesizes the findings. That is the rocket picture. This hierarchical integration requires that the integrating leader has sufficient expertise to be able to handle all partial contributions. It's transparent by whom conclusions are drawn, although the process through which is adopted by the various group members may vary. So if we look at puzzle solving efficiency, it's highly efficient for solving puzzles, given that the PI spans the entire span of problem solution. So it's very efficient for solving disciplinary puzzles. When it comes to the ability to locate loci of trouble, yes, there is division of labor, but there may be limited cognitive divergence if it's very clearly focused on the direction set by the PI, or there may be a lot of thinking along the same directions within such a rocket. And also the ability to raise concerns, raise questions may also depend on the hierarchical nature of the rocket, in how far the people in the fuel tank have to submit to to the direction set by the PI, when they had to defer to the direction set to the PI, or whether they have the freedom to come up with alternatives that may actually challenge the entire direction of the rocket. And that moves it into risk spreading. Since our new suggestions may actually be suggestions that change the entire direction of the rocket, that may be very difficult to get through in that kind of organization. And often it will not be an option to split the group and go in another direction if you belong to the fuel tank, or like it's an option for all the individuals or in a Kuhnian model to think, okay, I think this direction is more fruitful, so I'll go in that direction, although the others go in the other direction. People are more tied to the direction set by the PI in such an organization. If we then look at the interaction among equal experts, here there's interaction between group members in order to interlock or their contributions. That's the constellation of stars picture. There's a division of labor according to expertise, or they're not all experts in everything. That means that sometimes they may form what our social epistemologists call it heterogeneous consensus, where they agree in the same claim, but for different reasons. There's a room for that kind of divergences inside this kind of group. But it's not given from the outset how joint conclusions are drawn and by whom. And that may affect the ability to raise criticism and examine alternatives. So if we look again in puzzle solving efficiency, this kind of group is typically more efficient in solving interdisciplinary puzzles, or because you have these people are together with different, who bring in different cognitive resources. That also means that the ability to locate loci of trouble, or the division of labor is different, or labor is divided according to the various kinds of cognitive or expertise, and the cognitive divergence enables a scrutiny from different perspectives. And that also means when it comes to risk spreading, there is a possibility for suggesting different directions, but it may require renegotiation of what is the shared aim or joint commitment of such a group, and it may in the end split the group. However, that kind of group may more easily split than what is the case for the rocket kind of organization. So such an analysis seems to indicate that the two types of organization are better at different things. And this is also vindicated by recent empirical studies that, based on analysis of citations among the entire corpus of the Web of Science database, concludes that large teams develop and small teams disrupt science and technology, and flat teams drive scientific innovation. And I think there are further things to consider in comparing such models, and not just their impact in terms of citations. Let's consider again this rocket model for scientific teams. Typically, such a PI will end up with very high H indexes. And foundations focused on large grants often use that measure to justify that they have made the right funding decisions. They put their money where it received the highest return in terms of knowledge claims advanced and justified. But what if we look at the larger ecosystem, and not only the risk spreading mechanisms and whether it overlooks effects of distributing future promise? To assess whether this kind of distribution of funding optimizes science's ability to develop human competences and capacity for doing science, something that is actually also important for many foundations. Complementary indices seem to be needed as well, so that the fuel tank of the PhDs becomes something more important than just a consumable, something that also contributes to the advance of science by increasing the human competence and capacity for doing science. A first step could do what some foundations have actually already started doing. Some foundations set a cap on the H index, and argue that when H indexes get too large, that is almost questionable in itself. And instead they ask much more about having PIs describe their most important contributions and use that as a basis for selecting PIs instead of the H index. But further, another idea would also be to create new indexes, or to normalize index to reflect co-authorship. That is something that already exists, but is not so often used. And also a next step could be develop additional indexes, for example, indexes normalized to reflect human expenditure, for example, the amount of money used for salaries or amount of manpower months spent, or given the number of citations. These are indices that have not, to my knowledge, been developed. One could also think about indices that measure how well junior co-authors from such a rocket fare once they leave the rocket, compared to juniors trained at different levels of granularity or different kinds of organization. And to my knowledge, also this is a kind of measure that has not so far been developed. So to summarize what I have presented in this talk, Kuhn produced a very elegant argument about the essential tension that drives scientific progress. Convergent thought enables theories to be investigated in detail, but also ensures that loci of trouble are identified, investigated, and resolved either within the paradigm or by paradigm change. And divergent thought distributes risk in the community until a new convergence is established when crisis arises. And all this is enabled by a particular kind of education. But as science develops towards more collaboration, more interdisciplinarity, a higher volume of activity, larger groups, higher dependence on funding, more consideration of use, or this analysis does not necessarily hold unchanged. First, there are additional tensions to examine. Two of them I have briefly mentioned, or as something I have published on previously, that more collaboration challenges accountability and requires new practices for calibrating trust among collaborators. And more interdisciplinarity challenges quality control and requires new practices for assessment of research results. Second, the development towards more collaboration and more interdisciplinarity in different kinds of granularity, the increasing granularity, also challenges Kuhn's essential tension argument, and especially it challenges the distribution of risk, and it challenges the production of human competence and capacity for doing science, and it will require renewed reflection on funding practices, including development of new kinds of indicators. Thank you for your attention, and also thank you to the Danish Carlsberg Foundation that is supporting my current research.
Thanks so much to Professor Andersen. And now we move into Q&A. We have switched to a hybrid format, so we can have online questions and comments, or we could have questions and comments from the physical audience. If there are some first steps and first rejoinders, Theo, please go ahead.
Excuse me, I was trying to unmute my microphone. Thank you very much, Hanna. That was really interesting and enlightening in many respects. I was wondering about the compatibility of some of the things that you said with Kuhn's later approach to incommensurability, because he thought of incommensurability as a driver of progress. So instead of a radical break within a paradigm, you have a speciation, a new paradigm that comes off the older paradigm, and so on. And then you have isolation, and that enables the community to go deeper and focus on some problems exclusively, and so on and so forth. And I was wondering if that's at all compatible with what you said about the importance of interdisciplinary research, collaborations among people with very different skills, and so on. So it seems to me that what you said is much more compatible with Galison's ideas of a trading zone between different fields, as opposed to an exclusive emphasis on isolation and incommensurability. So perhaps you have a comment on that.
Yeah, definitely. I think that the route that Kuhn took later on, where he tried to extend the idea of incommensurability to apply also to the relation between different disciplines, I actually think is the wrong turn on Kuhn's part. I think these are two very different relations. I think the relation of incommensurability is a historical relation that says something about how a chain of reasoning is changing and having some radical changes as it goes through history. Whereas the relation between different and I mean, the crisis and the whole problem arises because they have a genuine discussion about who is right about something that they are perceive, or it's the same thing. I mean, this is the core of the whole realism debate, of course. What does the same thing mean? But the relation between different disciplines is very often of a completely different kind, and it doesn't contain the same kind of problem as the realism problem and the incommensurability discussion does. And I have been surprised that Kuhn wanted to take his argument in that direction, because it opens for so much of the initial criticism if you start also using incommensurability as describing the relation between different disciplines. That is not to say that the relation between different disciplines is something that can easily be solved, but I think that it's not fruitful to use incommensurability as a concept for describing that relation.
Thanks so much for the question and answer. If there are some more questions for joiners. If I may, let me interject a question of my own. I'm very new to all this, so this is going to be quite half-baked. Thanks so much for your talk. You critically assessed some indices. So for instance, you suggested that beyond a certain threshold, the H index is no longer that telling. And you suggested other indices that might be useful in assessing the research and innovation potential for research teams. And so naturally, for me, that seems to suggest that there might be principles to engineering innovation and creativity. And I was wondering if currently the research is at the stage of inspecting and observing regularities, or if there are experiments with respect to this. So if various values for these variables are tried out to see with what outcomes. And in particular, if this emerging field of engineering innovation is, in your view, reaching the status of science itself, or if it's still in the waters of science policy, of political decisions, and so on. Thanks.
I think that whole, I mean, I've seen a discussion in the literature about whether is this a scientific field or not. So you're really hitting on a debate that is out there. Or I have seen some bring the argument that we have seen really a proliferation of measures over the last decades, and given that there is very little agreement among the people in scientometrics or bibliometrics or whatever the field is called about the measures, seem to indicate that this has not yet reached the stage of a mature science. So that argument is clearly out there. I would also say that for a lot of the work done, there's still a lot of conceptual clarification to be made. Personally, I'm somewhat skeptical of those directions that try to make what they call field normalized measures. I have a background in physics, so I'm very familiar with the idea of field normalization. But field normalization in physics presupposes that you have a pretty clear definition of what a field is. And in scientometrics, or the definition of a field, is still very, very unclear. And some of the field normalization attempts, for example, draws their field concepts simply from whatever is done in the web of science, and that seems to be a very, very shaky definition of a field. And I realized that the way I presented it could be heard as if I'm a great fan of that kind of measures as such, and just want or some measures are to be replaced with others. That's not how I would like to present it. I think that in the move that we have seen towards more and more quantitative assessment and less qualitative assessment is actually also a problem for science. But being a pragmatist, I would also say, given that there is so much emphasis on the quantitative measures, then at least what we can do is to look at how they can be made better, even if perhaps personally I would prefer if we had much more qualitative assessment.
Thanks so much. And for what it's worth, I wholeheartedly agree. So next up, we have a question for Professor Chang. Hasso, please go ahead.
Hi, thank you so much, Hanne. Very, very instructive paper. And one thing that your talk and some similar work makes us realize is that Kuhn really said very, very little about the structures of scientific communities, right?
Yes.
He emphasizes community, but how is it organized? He says very little. So along that line, I wondered if you had some further thoughts about the structures of communication. So, bibliometric analysis and so on, they focus on publications, and rightly so, but science isn't just publication, and you get at the structures of research teams with the rocket model and so on. But is there something we can usefully analyze about structures of communication, ranging from how conferences are done to how papers are circulated? I mean, preprints are not what they used to be, yet they seem even more important than what they used to be, and so on. So I wondered if you had some thoughts about that.
I think that is clearly something that we ought to drive in to bring in as well. And I mean, circulation of preprints, for example, was also part of what Kuhn talked about when he talked about communities. That is, of course, also something that has changed dramatically in the meantime. And I think there's work that needs to be done on how it is that our scientists within a community select or define the boundaries of who they are and what they do. And the work I have seen done on that so far seems to come up with very divergent results. There are sociologists of science who have started investigating now that most research is easily accessible online, and people may search for literature in broad or databases instead of disciplinary databases. What does that mean for the way in which the literature clusters in communities? And some studies come out and say, well, as more and more things become accessible, people cite broader and broader. And others come out with the result that, well, as things become more accessible, people cite more and more narrowly. So there's an open question there that needs to be explored. I think also you're absolutely right in pointing to conferences or as a venue for communication, or that we haven't addressed very much. I know of a few historians who have looked at conference participation in talking about who are core members of a profession. but it hasn't been done very much. And I think that that will also be an important ingredient in that kind of structural examination of science.
Yeah, thank you.
Thanks so much. And I don't think it's by accident that the question and answer were given by the two keynotes for today. If there are some more questions, comments, or joiners. If not, please join me in thanking Professor Andersen for her talk.